Welcome all. In the last lecture, we talked about the fact that if G is a group given to you, that is sigma 1, sigma 2, so on, sigma n, which is a subgroup of automorphisms of K, and F is its fixed field, then degree of extension of K over F is exactly equal to cardinality of G. Okay, so now we will use this result to establish some more result which are quite essential in the upcoming videos. So the first result that we are going to talk about is this. Result number 1. Let K over F be finite extension then cardinality of automorphisms of K over F is less equal degree of extension of K over F, and it further says that equality holds if and only if F is the fixed field of out of K by F. Now we'll try to prove this. See, proof is quite easy. What we'll do, first of all, we'll assume that suppose F1, we have a group automorphisms of K over F, right? So suppose F1 is the fixed field of F1 is the fixed field of out of K by F, right? So in the last theorem that we have already talked in the beginning of this video, we can see this is our G and this is our fixed field F, okay, and this is our field K. So using that result, we can write that this implies degree of extension or number of elements in group, that is automorphisms of K over F, is exactly equal to degree of extension of K over F1, okay, because F1 is the fixed field of that group. Now diagrammatically what will happen, this is your K, this is our base field F, okay, it is a finite extension and F1 is fixed field of out of K by F, so F1 lies in between K and F. So this is extension diagram, right? So using this extension diagram, what can you write? Clearly, degree of extension of K over F is equal to degree of extension of K over F1 into degree of extension of F1 over F, right? But degree of extension of K over F1 is equal to cardinality of out of K by F. So this implies degree of extension of K over F is equal to cardinality of out of K by F into degree of extension of F1 over F. Now it is quite evident that F1 lies in between K and F. So degree of extension of F1 over F will be either 1 or greater equal 1. So this is greater equal 1 basically. So that's why we can write. So this implies cardinality of out of K by F is less equal degree of extension of K over F. Reason is because degree of extension of F1 over F is greater equal 1. Okay, now when equality holds mainly when this is equal to 1. Now equality holds only when degree of extension of F1 over F equal to 1, that is F1 equal to F. But F1 equal to F, that means because F1 is assumed to the fixed field of out of K by F, so if F1 equal to F, that means F is the fixed field of out of K by F. So this implies equality holds if and only if F is the fixed field of F is the fixed field of out of K by F. But we can also find that if equality holds, that statement can be written like this, that is degree of extension of K over F is exactly equal to cardinality of out of K by F, but such extension is called as Galois. So extension is Galois if and only if, that means K is Galois extension of F. If F is the fixed field of out of K by F, that can be other version of this particular statement, right? Because it is quite simple. Equality holds, that means this is true. But if equality holds, it is possible if and only if F is the fixed field of out of K by F. So that means this implies K is Galois extension of F if and only if F is the fixed field of out of K by F, right? Now we will move to the result 2. Let G be a finite subgroup, finite subgroup of out of K, okay? And F be the fixed field of G, okay? Then every sigma belongs to out of K, then sigma belongs to out of K, automorphism of K such that it fixes F, that is sigma of F equal to F belongs to G. So every automorphism of K which fixes this field, fixed field F, belongs to G. Okay, so that's what we need to prove now. So proof is quite simple. Let's move to the proof. What is F? F is the fixed field of G, right? So basically, since F is the fixed field of G, G is gonna be subgroup of out of K by F because G fixes F, right? But basically all these automorphisms means if I consider set of all automorphisms of K over F, this is collection of all automorphisms that fixes F, right? And G also fixes F, that means G is gonna subgroup of this particular automorphism too, right? Because this is collection of all automorphisms that fixes F, and G again fixes F, that means G is subgroup of this out of K by F, right? So if G is subgroup of this out of K by F, cardinality of G is definitely less equal cardinality of out of K by F, right? But what we have seen here that G is a subgroup of out of K and F is fixed field of G. So if we use the result means theorem that we have said in the beginning itself, we can simply write we have number of elements in group is equal to degree of extension of K over its fixed field, and its fixed field is F. So cardinality of G is equal to degree of extension of K over F. Okay, so if I will put this value here, so what will happen? So degree of extension of K over F is less equal cardinality of out of K by F, right? But we already know that cardinality of out of K by is less equal G. Cardinality of out of K over F is less equal degree of extension of K over F, which is G actually, that is equal to G. So if we combine these two statements, this clearly implies that cardinality of out of K by F is exactly equal to degree of extension of K over F, and that is equal to cardinality of G, right? So all the automorphisms that fixes F belongs to G. Okay, so that's the result. Now we will go to the next and final result in this particular sequence, after which we will go to the important theorem. So this is result number 3. Result is quite simple. If G1 is not equal G2, okay, then F1 is not equal to F2. G1 and G2 both are subgroups of automorphism group of K out of K. Then F1 is not equal to F2, where F1 comma F2 are fixed fields of fixed fields of G1, G2 respectively. So what does it mean? It means that if subgroups are distinct, then their fixed fields are also distinct, and this particular statement is quite essential in the fundamental theorem of Galois theory, because when we define a map, one correspondence between subfields of K containing F and subgroups of G, then definitely this is gonna help us. Okay, so that's why if subgroups are distinct, then their fixed fields are distinct, but we will use contrapositive to prove this. So we will prove that if fixed fields are same, then subgroups are same. So if f1 equal to f2, then obviously f1 is f2, but f2 is fixed by g2, right? So then f1 is fixed by g2, but originally f1 is fixed by g1. Okay, g2 also fixes f1, but basically f1 is fixed by g1. Okay, so definitely by previous result, this implies g2 is subgroup of g1. Similarly, f2 is fixed by g1, right? F2 is, because f2 is equal to f1 and f1 is fixed by g1, so f2 is also fixed by g1, but basically f2 is fixed by g2. Okay, so f2 is fixed by g2, so g1 is less equal g2, because g2 gonna be larger subgroup than g1, which fixes f2. That's it. So this implies g1 less equal g2, that is subgroup of g2. So if we combine these two statements, hence we can easily say that G1 equal to G2. So if fixed fields are same, then subgroups are gonna be same. So it clearly implies that if subgroups are distinct, then their fixed fields are also distinct. Now we will move to one important and very essential theorem before going to the final proof of fundamental theorem of Galois theory. So that theorem reads like this: K over F is Galois, means K is Galois extension of F if and only if K is splitting field of K is splitting field of some separable separable polynomial over F. Now let's go for a proof. One part of proof is quite easy. We have already proved that if K is splitting field of separable polynomial, then K is Galois extension of F. That result have been already established. Okay, so suppose K is the splitting field of some separable polynomial over F. So this implies K is Galois extension of F. K is Galois extension of F. Because in this case, since polynomial is separable, all its roots are distinct, so we will get exactly the same number of automorphisms as of degree of extension. So that's why K is Galois extension of F. Now let's go for converse part. Conversely, suppose that K over F is Galois. That means K is Galois extension of F. Now I want to prove that K is a splitting field of some separable polynomial. Okay, so how I'm going to start it? First of all, I will consider one irreducible polynomial over F. So let me just draw here a diagram for better understanding. So let me write this K, and this is my field F. Okay, and this is extension. Okay, this is extension given to you. Now what I will do, I will consider one polynomial P of X, which is irreducible polynomial defined over F. Okay, and suppose one of its root is in K. One of the root of P of X is in K. So P of X is irreducible polynomial. P of X is irreducible polynomial with its root in K. Say alpha is a root of P of X and alpha belongs to K. Fine. Now what I will do, I will take alpha, right? And then we will apply the elements of G. G is nothing but elements of Galois group of K over F. So I will apply elements of G, Galois group of K over F over alpha. So identity is gonna apply. So identity then alpha. Then I will apply sigma 2 of alpha. Then I will apply sigma 3 on alpha, sigma 3 of alpha, so on sigma n of alpha, right? So all these were, let me just write, because this all again belongs to K, because these are automorphisms of K, right? So where sigma 2 identity map, sigma 2, sigma 3, so on sigma n all belongs to Galois group of K over F, because K is already Galois extension of F. So Galois group of K over F, so all these elements belongs to Galois group of K over F. Now what will happen, we have alpha. Now sigma 2 of alpha will be something, it will be some element of K. Again sigma 3 of alpha going to be some element of K, and rightwise sigma n of alpha is going to be some element of K. So what I will do, we will just exclude the repeated elements here, and we will only consider distinct elements. Okay, so let alpha 1, alpha, so that is basically alpha, because let me just write here. So let alpha 1 that is equal to alpha, then alpha 2, and so on, say alpha r. Okay, so suppose all these elements belongs to K are distinct. Okay, so out of the previous list I have only chosen distinct elements alpha, alpha 2, alpha 3, and so on alpha r. Now what I will see, I will see what happens if I apply any other element of G on these elements. So we'll take some tau, let tau belongs to G, which is Galois group of K over F. And suppose we apply this tau on these elements alpha, then I will apply tau on sigma 2 of alpha, then I will apply tau on sigma 3 of alpha, and then I will apply tau on sigma n of alpha. But what happens basically, G is a group, right? So actually after applying this, we will find maps like this. So we have tau, then we have tau sigma 2, then we have tau sigma 3, and so on, we have tau sigma n. But G is a group, so this set is again equal to E sigma 2, sigma 3, and sigma n. So what actually tau does, tau only alters the position of these elements. Okay, so tau does not give you any new element, it only alters the position of these elements, or we can say tau permutes these elements. Okay, so if tau permutes these elements, that means I can consider a polynomial. Suppose I consider suppose f of x equal to, say, x minus alpha, then I will take another factor x minus alpha 2, then I will take another factor, so on, x minus alpha r. Okay, and if I apply tau on this f of x, nothing is going to happen, only these factors will alter, because tau only permutes these elements. Okay, so factors will have some different arrangement, but factors will be same. Okay, and this happens for every element of G. So that means every element of G, every element of G fixes f of x, means it fixes the coefficients of f of x. But what is the fixed field of this G? G is Galois group of K over F, and K is Galois extension of F. So we have seen it previously also in the second result, that if G, we can see here the result 1, K is Galois extension of F if and only if F is the fixed field of out of K by F. So here, since already K is Galois extension of F, F is the fixed field of out of K by F, right? So that's why, since any tau belongs to Galois group, applied on f of x fixes f of x, that means it fixes the coefficients. So all the coefficients must be in the fixed field, and fixed field is f. Okay, so I can write here as every element of G only alters the factors, comma, Coefficients are fixed by G. Coefficients are fixed by G, right? Coefficients are fixed by G means they are in the fixed field of G. But since it is Galois extension, fixed field is F. So coefficients are in F. So this implies F of x belongs to Fx. So f of x is a polynomial over fx, right? Now what is p of x? P of x is already assumed. P of x is irreducible polynomial and its root is in k. Alpha is the root of p of x in k. It is irreducible. That means it is minimal polynomial of alpha. And f of x has also alpha as a root. So definitely p of x divides f of x because p of x is going to minimal polynomial. So clearly p of x divides f of x, right? Because it is because p of x is minimal polynomial of alpha. Also, f of x divides p of x because f of x, every factor of f of x is a factor of p of x, right? Instead, we can see here p of x has only one root alpha. We took all these n elements and after that we remove the repetitions and we only consider element which was not repeated, right? So definitely what does it mean? It means that f of x has less number of factors than that of p of x. Okay, but all the factors are common. So every factor of f of x is a factor of p of x. So f of x divides p of x. Okay, so this implies since both the polynomials are monic, this implies p of x equal to f of x. And since all the roots of f of x are separable, distinct, that means p of x is separable. So this implies p of x is separable because all its roots are distinct. So p of x is separable and all its roots are in k. So this happens for every irreducible polynomial with root in k. Okay, now we will go to the actual proof that we want to prove that k is splitting field of some separable polynomial over f. So how we are going to do it? So let me just once again draw a diagram. So k is your extension of f and this is finite extension. So let us assume that basis is finite. So let me take omega 1, omega 2, so on omega n as basis, right? So omega 1 is element of k, omega 2 is element of k, omega n is element of k. All these elements are of k. So you'll find minimal polynomials of these elements over here. Okay, so suppose omega 1 has minimal polynomial, say p1 of x. So p1 of x is irreducible and one of its root, that is omega 1, is in k. Okay, so it clearly satisfies the conditions of p of x. So it is going to be separable and all its roots will be in k. Similar thing will happen with omega 2. So if I assume that minimal polynomial of omega 2 is p2 of x, then again p2 of x is irreducible. Its one root omega 2 is in k, so all its roots are in k and it is separable. And same story will repeat for each and every element of this basis. So omega n, if I assume that minimal polynomial is Pn of x, then again Pn of x is irreducible, its one root omega n is in k, so its all root are in k and it is separable. So what we will do, we will consider polynomial g of x, but g of x, consider g of x, g of x will be product of all these polynomials but after excluding the repeated factors. P1 of x is separable, none of the root of P1 of x is repeated, none of the root of P2 of x is also repeated, but when we take this product, it is possible that some of the roots might be repeated. So that's why we will delete those roots, we will delete those repeated factors and we'll only consider g of x after removing all the multiple factors of product. So g of x is polynomial obtained by removing multiple factors, removing multiple factors of p1 of x, into P2 of x, so on Pn of x, right? Now g of x is separable because all its roots are distinct, because we have removed multiple factors, so all of its roots are distinct. Okay, and all the roots are in k. Okay, so that means g of x is separable, all its roots are in k, that means k is a splitting field of g of x. So k becomes splitting field of separable polynomial g of x. Thus k is a splitting field of separable polynomial g of x, and that's what we wanted to prove. So this result have been established now, that extension is Galois if and only if k is a splitting field of some separable polynomial over here. So we have collected so many things together, right? Until now we have discussed Galois extensions and we have collected so many things together. So we are now in position to write some characterizations of Galois extension. So how can we identify whether a given extension is a Galois extension or not? So after this much analysis of Galois extensions, we can characterize Galois extensions, right? So what will be the first character that we have seen? That just now we have seen it. Galois extensions are a splitting field of separable polynomial. Okay, so let's talk about k over f. So first thing is that k is splitting field of separable polynomial. That is the one characterization of Galois extension. Secondly, it is going to be finite extension, right? It is a splitting field, so it is normal extension. Okay, and it is a splitting field of separable polynomial, so it is separable extension. So second characterization, which is quite important, that k is finite, normal, and separable extension of f. Then third characterization is nothing but the definition of Galois extension, which we have taken, that coordinate of automorphisms of k over f should be equal to degree of extension of k over f, which is the original definition of Galois extension. And last characterization, which we have established, okay, in the result one, that k is Galois extension of f if and only if f is the fixed field of k over f. Okay, so k, or we may say fixed field of out of k by f is f. So using these characterizations, we can identify whether a given extension is Galois extension or not. In the upcoming video, we will talk about fundamental theorem of Galois theory, because we have established all the necessary background which is required for the proving that theorem. So in the upcoming video, we will deal with fundamental theorem of Galois theory in detail. Stay tuned. Thank you.